Hello everyone, welcome to my chemistry channel B.L.Dash, short and sweet in chemistry. Now the chapter is short revision in electrochemistry and it is the topic Color's law, electrolytic cell and electrolysis. This is part 14 and for class 12. Now again we want to discuss about the chapter 13 A, B, what we learn. In strong electrolyte, it is very ionizable, and here in solution is the ionization that is complete. In strong electrolyte, so the limiting molar conductivity, that is lambda m, molar conductance at infinite dilution, and here what happened can be determined from the graph. I told in the part 13b, molar conductance at particular concentration versus root over Xi by extrapolating it at zero concentration. Then when you put the graph, that is molar conductance versus Xi half root Xi for KCl, KCl is a strong electrolyte. In solution, the ionization is complete. And for weak electrolyte, what happened? The limiting molar conductivity that cannot be determined by the extrapolating the graph to zero concentration. Why? Because the weak electrolyte cannot be ionized completely, and so from graph we cannot calculate concentration or molar conductance from the graph. When the concentration approaches to zero, what does it mean? That means at infinite dilution, the graph becomes almost parallel to the y-axis. Now, when the concentration approaches to zero, that means infinite dilution, the graph here you can see this is parallel to the y-axis. So, limiting molar conductivity of weak electrolyte, example what? Acetic acid may be obtained by one law, that is indirectly you will calculate by the help of the law, Color's law. And here the Color's law, what is that one? That Color's law examine molar conductance at infinite dilution, or you can say zero concentration, values of a number of strong electrons observe certain regularities. Now by this law, the molar conductance for infinite dilution can be calculated easily by for the strong electrolyte. It's easy. He noted the difference in molar conductance at infinite dilution of the electrolytes, just as NaX and Kx. Na means sodium, X means any halogen. So you can say NaCl, KCl and different. X is nearly constant. X is constant one, and Na, so sodium, potassium and metal, they are different. For example, the temperature should remember, it should be this is the 298 Kelvin. The pairs of strong electrolyte where the having common cations, what are the values it is you got? See, this is for KCl. KCl, this is molar conductance and infinite dilution calculated from the Color's law, that 149.86. Similarly, NaCl 126.45. I told when the cation, this part, they are same except the halogen. A halogen are same except that metal. One is potassium, another is sodium. Since halogens are same, so difference should be here. Value what you get, you take another one where Kna and Br. See, this halogen is chlorine, this halogen is bromine. Then what happened? Difference. The difference also same, 23.41. Here 23.4. That means what you learn from here? When the sodium, potassium, the metal ion, they are same and they are different for same halogen, and what is the difference you will get? Both are remaining same. This is the same, that is 23.4. Similarly, KNO3, NaNO3, KNO3, NaNO3, one here also you can observe, and this is NO3, NO3, and same, and here value that is 23.41. Here also you are taking K, potassium, and Na, sodium. So if the anions are same and here cations are same, but in both case different, then what happened? The value difference is remain same. Similarly, when having same cation, here having same, and this example NaCl, KCl, KBr, NaBr, KNO3, NaNO3. When same common cations, then what is the result? Common cations mean KK. See in this case K same and here K same. Only halogens are different. When the value difference you want to calculate, this is 2.06. Similarly, when the cation both are same, here what happened? This is Br and this is Cl, just above. Above you can observe Br, Cl, and it is only K same and only Na same. So here you should see if it is potassium, and for one case and for other case it is also potassium, but halogens are different. So here when you see what is the case I told, difference is 2.6. 2.6. Other example also you can get here. This is one example, let us see 2. Then here KBr, KCl, NaBr, NaCl. Other example NaBr, NaCl. Na, both cations are same, that halogen, that anion same, Br, Cl. That means here in one case Br, other case Cl. In second example, one case Br, second case Cl. And here you can observe the cation same Na and anions, that other case cation same K. In one case Na, other case K, but halogens are same, so results also are getting same, difference 1.8 and 1.8. And here what happened, if you calculate the difference that is same, then how the Color's law is helpful for independent migration of ions. Now when you see that molar conductance for a strong electrolyte, for a weak electrolyte, for strong electrolyte, what happened, that is clear to you. Now we will see how it is helpful, Color's law in strong electrolyte. In strong electrolyte, you know the electrolyte that is ionized completely, 100% completely ionized, and the law states that limiting molar conductivity of an electrolyte can be represented as the sum of anion and cation of the electrolyte. That means every electrolyte having cation anion, and then molar conductance of cation, molar conductance of anion, the sum that represented limiting molar conductivity of electrolyte. Now, practically it is also proved. And now if lambda 0 Na plus, molar conductance of Na plus and molar conductance of Cl minus are limiting molar conductivity of Na plus and Cl minus. What indicates this lambda 0? 0 means at infinite dilution. Na plus means cation. Here Cl minus means anion. And then how to calculate the limiting molar conductivity of the strong electrolyte? That example here, molar conductance of NaCl. See here, conductivity of NaCl is given by molar conductance at infinite dilution equal to the cation and plus anion. Molar conductance of cation and molar conductance of anion. But remember, you are not now here not represented how many cations are there, how many anions are there. Then here you should represent that V plus cation, that is number of cation, and V minus number of anion. So in this equation, this let it is 1, and in equation 2, what is the difference? Here you are putting number of cations, number of anion. V plus the number of cation, V minus the number of anion. And V plus means the cation molar conductance. This is anion molar conductance. So here the molar are the then it is the lambda plus 0 and lambda 0 minus. They are the molar conductivity of cations and anions respectively. And then what happened here? The example, it is calculated from the experiment. Na plus, that is the cation value, what is the molar conductance of this value, and it is written. If necessary, you can remember, but sometimes it is very helpful to us. That is why minimum sodium chloride, KVR, and this one example you should remember for any representation. So Na plus 50.1, Cl minus 76.3, K plus 73.5, Br minus 78.1, Ca plus 2. When you can remember, when the size of the cation anion increases, then here also the value of molar conductance increases. And so here you can get these are the values. Experimental value that you are getting is molar conductivity of cation and anion respectively. Then here for weak electrolyte what happened? Now till now you know about strong electrolyte. Again you see strong electrolyte completely ionized. Here V plus the number of cation, V minus the number of anion. So how to calculate molar conductance of the strong electrolyte? The number of cation having that molar conductivity of cation plus V minus, that is number of anion, lambda that is plus, that is for anion, lambda minus, that is for anion. So when you add or make a addition of the molar conductivity of cations and molar conductivity of anions, you will get the molar conductivity of the strong electrolyte or electrolytic solution. Weak electrolyte, what happened? You know, weak electrolyte not ionized completely. So example acetic acid, where you will get lower degree of dissociation, mean here dissociation or ionization is not completed at higher concentration. Also for such electrolytes, the change in molar conductance or dilution. Then how it change? That is due to increase of degree of dissociation. Means used to weak electrolyte, when diluted, here the degree of dissociation also increases. Then consequently the number of ions in total volume of the solution that contain 1 mole of electrolyte. That means here number of ions also increases. Then here at infinite dilution what happened? Concentration, that is 0. Concentration 0 means that you can say infinite value. The electrolyte dissociate completely. For what? For weak electrolyte. That means when it is dilution. And see in strong electrolyte what happened? It is already completely dissociated from the beginning. So at infinite dilution remains same. When alpha, the degree of dissociation is 1, that is for what? For weak electrolyte at high dilution. Then here when concentration is 0. But at such low concentration, the conductivity of the solution so low that it cannot be measured accurately. Now the here completely ionized, number of ions may be, it cannot be. So the conductivity of solution is low. But such low concentration become dilution, Here the molar conductivity of the solution is low. It cannot be measured accurately. Now in strong electrolyte happen, the molar conductivity easily calculated, because for cation it has specific value, for anion has specific value. By making addition you get the molar conductivity of the solution. But in this case low concentration, what happened here the conductivity is low because it cannot measure accurately, for the ions, that is why. So molar conductivity for weak electrolyte is obtained by using. So how can you get that molar conductivity of the weak electrolyte? By using that law, Color's law of the independent migration of ions. Color's law, what to do, because a weak electrolyte not completely ionized, and you cannot get the limiting molar conductivity of all the cation anions. Then here what to do, at any concentration C, the alpha is the, if alpha is the degree of dissociation, then what happen, alpha can be approximated to the ratio of the molar conductivity. Then what is the degree of dissociation? That molar conductance at particular concentration, and molar by divided by molar conductance at zero concentration, or you can say infinity dilution. So this is for weak electrolyte. See, when you see for the strong electrolyte, these are getting one value, and for weak electrolyte having particular value, you put and do the calculation. Then how to making simplify? Here degree of constant value. Here what you get, C alpha square divided by 1 minus alpha. Dissociation constant, K is the dissociation constant. Then what happened, this is the value. Then what happened, C you know the value, and alpha square you know this value put this one, and here delta 0. Then here what is alpha? Alpha equal to 1 minus molar conductance at a particular concentration divided by molar conductance at 0 concentration, you can say infinite dilution. So here alpha equal to, here you see you can see put here C also, no problem, and then it is this square, all cancelling each other, then you will get this value. This value mean you say C concentration, molar conductance square divided molar conductance at 0 concentration, and multiplied by molar concentration at 0, and minus that is molar conductance at particular concentration. Then here after putting all the values you will get the answer. What is the question with molar concentration, molar conductance, or the value Ka? All the question that can be solved by this formula. Then what are the application? What are the main important for the Color's law? By using Color's law of independent why it is told as independent migration of ion? Because the ions having particular molar conductivity. Though in weak electrolyte it cannot be calculated properly directly, but it can be calculated indirectly by the formula. It is possible to calculate molar conductance at infinite dilution for any electrolyte from what? From alpha. Alpha means that is independent ions. Alpha 0 molar conductance of individual ions. From that value you can calculate molar conductance for the electrolyte. And here you are sure that this electrolyte only may be possible for the strong electrolyte. For weak electrolyte like acetic acid, it is possible to determine the value of its dissociation constant. And before that, I told this formula. See this formula: Ka equal to C alpha square minus divided by 1 minus alpha. By putting all the value, you can calculate degree of dissociation. And here, if you know molar conductance at a infinite dilution and molar concentration at a particular molar conductance at a particular molar conductance at a particular concentration, then one can calculate. Suppose one example, say this is very important example, and here conductivity is given, but it is acetic acid, that means weak acid. Weak acid, what to do? See here, calculate the dissociation constant if this value is given. What are the value given? Remember here, then you put the value. You know lambda m, that is molar conductance of the electrolyte divided by K divided by C. K, what is the Kc? That is conductivity, kappa. Kappa, this is given, and here concentration also given 0.001028. After dividing, you are getting this value 48.5. What is this? This is molar conductance. And here, what is alpha? I told alpha equal to molar conductance of particular concentration divided molar conductance by infinite dilution. These two values is given. One here it is given, that is 390.5 for infinite dilution, and this is a particular concentration 48.5, and the value is given. So what is K mean dissociation constant. Calculate the dissociation constant. Here it is K, and here it is, that is kappa. So it is kappa and it is K. Ka, right? Ka, degree of dissociation constant equal to this value. You will get the answer after solving the equation. So dissociation constant is given 1.78 10 to the power minus 5 mole L minus 1. So how to get that molar dissociation constant? If you confuse, then write Ka, the dissociation constant, the values come to here. And I hope the Cauchy's law application, weak electrolyte dissociation and strong electrolyte dissociation. What is the difference between dissociation constant of strong electrolyte and weak electrolyte? How to calculate? All things I have explained. I hope it is clear to you. Myself B.L.Dash, PGT Chemistry, ex-PGT Chemistry, Kendra Vidyalaya Sangathan. Please subscribe my channel, Short and Sweet in Chemistry, B.L.Dash. Thanks for watching my video. Thanks again to all.